Okay, so let's see the third reactor, which is the Gibbs reactor. And as we mentioned before, the Gibbs reactor is a thermodynamic, pure thermodynamic calculation reactor. Let's call it Gibbs first. So it does thermodynamic calculations just to minimize the Gibbs free energy according to the inputs that you specify. Let's just call it the product of the Gibbs. Again, let's see the inputs. It's going to be different now. So in the first two reactors, the stoichiometric and the equilibrium reactors, I had to define the reaction. I do not need to do this now. So you can ask it to calculate the phase equilibrium only, just to check if it's one phase or two phases, or calculate phase equilibrium and chemical equilibrium. So it's gonna change the compositions of the products of the feed to the reactor to minimize the Gibbs free energy, or to restrict chemical equilibrium. So you'll define a reaction, and you can make it kind of operate like the equilibrium reactor, and the same here to restrict chemical equilibrium. We'll go through these now. So if you go through the phase equilibrium, you'd find that this tab was active. Now it's not. So some tabs here are not active. You specify the pressure of 1 atmosphere and the output at the temperature of 75 degrees Celsius. And you can define the number of fluid phases. I can put it 1. But if you put it 1, it's gonna give you a consistency error, because there is no way you can do phase equilibrium if you have only one phase, because you have to have more than one phase to do equilibrium. So minimum you have to have 2 phases. And if you run the file, you'll find that the results are gonna be just the balance. That it's usually what we have. You have no energy in because you didn't do any calculations. For the balance, you have nothing, the same in, the same out. For the phase composition, this is the mole fractions of the feed. So you have nothing coming out of the reactor that is different from what you have in the reactor. The same mole flows in and out. So I can see that this is not a very useful option actually, because you're not gonna get anything out of it. The second is gonna be useful. So now you have the phase equilibrium and chemical equilibrium. I'm not defining any reactions now, but you can give it some hints about the outputs that you need to get out of the reactor. So you can say that the reactor will consider all the components as products. All the components, what I mean by all the components is the components that I defined in the properties environment, what we do in the very first step after starting the file. Or you can identify the products. You tell him that not all, because you might have a very big flow sheet with a lot of streams with different components, and not all of them are included in the reactor. So you can specify which should be coming out of the reactor. Or you can define phases if you want. I'm gonna consider all the components because I have only the 4 components here. So you can also assign the phases to the streams. So I can tell him that if I have more than one output stream, I can tell him for this stream I have this phase, and for this stream I have this phase. You can define the inerts if there are some components that are not included in the reaction as inerts, solids or inert gases or whatever. You can put it here. But let's see what we're gonna get out of this. For the results, you can see that you have here some duties. It wasn't there before. Number of phases is going to be 1. The balance is the same, number of moles and the masses. And the phase composition, this is the output phases that you're going to get. And for the atom matrix, it's going to give you the number of atoms of hydrogen in each one of them, and the carbon and the oxygen. And this is nice. And for the stream results, this is gonna tell you how much of the reactant is or the feed is reacted. So you have 186, this gives you 59. It's similar to what we got before. It's reached equilibrium, but you didn't define a reaction, so it's not gonna give you any information about the rate constant or anything similar. For the third option, if you restrict chemical equilibrium, you will see here that this tab is now active. Okay. And this is gonna tell you that the temperature approach, it will be 0. You can define this, or you can define the reactions. So it's gonna consider that there is a chemical reaction that takes place at the same temperature, or we'll do this. So again, let's go for the first option first, and then see the outputs, and then go for the second and see the outputs. So you'd see no difference in what you're gonna get for the stream results here. It's almost gonna give you the same output. It's kind of different, but yeah, it's the same output for the mold flows. So it's not gonna be different from the option that we defined before. The only option that you're gonna get out of here is that you can define another temperature to work in, which is, it's okay. Anyways, for the reactions, you can define the reaction the same way that we defined before, the ethanol and ethyl acetate. -1 and -1, and you get water and ethyl acetate, and this is going to be 1 and 1. The temperature approach is 0. Oh, it defined 2 reactions, so we can get rid of this, delete the row. And this should be okay. Or reaction numbers between, oh, should be 1. So this is because it's number 1, so it's not happy for that. So we need to put this as 1. Anyways, I think I have to start from the beginning, delete everything. So this is gonna be ethanol. Sometimes it's stupid in some cases like this. You have it cannot let you change the number of the reaction. The water is 1 and the ethyl acetate is gonna be 1. The temperature approach is 0, so should be good to go. And let's run the file and let's take a look at the outputs. It's gonna be the same, but we have here the K equilibrium, which is gonna give you the same number that we got before. So you can use the Gibbs reactor as an equilibrium reactor if you define the reaction. So this is kind of a very useful piece of information actually. And you can do the same thing for specify the duty temperature and the temperature approach, and this is what you're gonna put here. If you put the duty as like 200 calories per second, whatever, so it's gonna be operating at another temperature. The results would be different. So this is the temperature, the balance, the phase equilibrium. It's not different from what we got, but of course you're gonna get different output compositions than what you got before because you're operating at different duties. So this is gonna change everything. So I personally prefer or find that this reactor is useful if you do not know the reactions. You need to know from thermodynamics what is the output. Again, this is gonna turn your reactor into an equilibrium reactor, so it's not gonna add more than what the equilibrium reactor would add to you. So this is all for the Gibbs, and in the next video we will go through the last one, which is the yield reactors. So let's see you then.